So everything I'm about to go through with you has been taught to you before, but I figured, heck, let's just get back and refamiliarize ourselves with the complex numbers. So in case you've forgotten what is a complex number, do any of you remember what a complex number is? That's okay. There's going to be a lot more that we learn. So this today and tomorrow bit is just for the stuff you already know. So complex numbers, hopefully you'll recall, are of this format, a plus bi. Does anyone remember anything about what I is? It is an imaginary unit, right? So I has a very specific value. It's like the square root of -1, right? And so examples of complex numbers are things like 3 minus 4i, right? And you might recall that at one point I showed you how to graph those. And you don't use regular, like, it's not like graphing a y equals mx plus b. It feels kind of similar, but you're in a different plane called the complex plane. You'll remember that the sideways axis was called the real axis, and the vertical axis was the imaginary axis. So at the end of the day, it's very simple. If I said, hey, Bloomer, I need you to graph this, she'd go, okay. She'd go right 3 and down 4, like, logically, like you would assume. But we're going to be studying the vectors. So not today, but eventually we're going to be studying the vectors that represent these complex numbers, like points in the plane. So do you guys do any vector stuff before you get to this class? In science? Right. Okay, cool. Well, that'll help a little bit. So anyways, that's a complex number. Another example of a complex number would be something like -8i. What's the real part of that complex number? No, doesn't have one. It's 0. So the real part is this number right here. That's the real part. And this part over here is called the imaginary part. So if a complex number comes at you looking like this, it's what we would just call a pure imaginary number. Okay. Is this a complex number? It is. Everything is a complex number. Okay. We sometimes just don't recognize or identify it as such, but a complex number like this has a real part of 4. What's its imaginary part? Yeah, it doesn't exist. And so this, if you graph this on the complex plane, you would never go up or down into the imaginary up or the imaginary down. You would just stay on the real axis. A number like this that has no imaginary part is called, you guessed it, a real number. So hopefully it's just kind of, like riding a bike. Once we get into the how to do all this stuff, it won't be all that bad. That's what a complex number is. It consists of 2 parts, a real part and an imaginary part, and it gets its very own set of axes when we go to graph it. The complex plane is what we call that. Do you remember any of this from a while back? Okay. Anybody remember any of this from a long time ago? A little bit? Nice. Cool. All right, so running down the list of things I want you to be able to do, that like by the time Tuesday's over, tomorrow's over, I want to be able to say you can do this, 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 and this. The first thing on that list is I want you to be able to find the modulus of a complex number. So the modulus, M-O-D-U-L-U-S, is kind of like the absolute value. So it's exactly how it's going to feel. And the notation looks exactly the same. So if I gave you a complex number like 4 plus 6i, and I asked you to find its modulus, the notation is going to make you want to say what's the absolute value of the complex number, but it's called the modulus. And the modulus is, quite frankly, it's the distance, if you will, from the center of the complex plane to the complex number itself. So if we were to graph this one, how would we get there? How would you get to 4 plus 6i? Perfectly spoken. We're going to go right 4 and up 6. And so it'll be someplace like up here. So just like anything else, when you plot a complex number, it just looks like a dot. It's like a point. So the modulus is represented by this line segment from here to here. And you might remember from all of geometry, it's probably fresh in some of your minds. How do we find the length of a crooked line segment like that? Like listen, if I said what's the distance on this red line, like from here to here, you'd have no troubles with that, right? Because you can literally count horizontally and vertically. Where's the difficulty in counting the distance of a diagonal line? Fair enough. What else? I mean, like, can you just count that out? Like, even if I put this on graph paper, which I don't have it on graph paper, could you count the diagonal distance? You cannot, because diagonal distances don't play nice. So like if you had a square that was 1 by 1, you can count one sideways and you can count one. But if you go across, does anyone know the length across a 1 by 1 square? It's the square root of 2. So it's around 1.4. So the rub on this is like, okay, if you want me to find the length of that red line segment, then you need to give me a bigger tool than just counting like a 10-year-old. Anyone remember the tool we use for that? Starts with a P. I'm not going to tell Mr. Manlove about this. Here, let me have some stuff for you. It's not pi. That was pretty awesome, though. That was rad. Just start saying things that start with P. Can you see my yellow triangle? Did you say it again? Who said that? Yeah, the Pythagorean theorem. Very good. So if I wanted to find the length of that green line segment, I can just use the Pythagorean theorem. And so that is that if this is like A and this is B, then I can just do A squared plus B squared equals C squared, right? How long is A in this case? So I just go 4 squared. How long is B? 6. And so I just do 6 squared. And then I add those together. And then what's the final step when working with the Pythagorean theorem? Square root. Very good. If you're very literal about A squared plus B squared equals C squared, then you'll see where this comes from. You know, A squared is 4 squared, which is 16. B squared is 6 squared, which is 36. But if this still equals C squared, to solve for C, you have to square root, hence the square root. So the answer to this problem is the square root of 52. And gosh, I hope you remember this. What do you do with a square root of 52? How do you break it down there, Coop? You can make a little tree. Absolutely. That's one way to do it, is to make, did you say tree? Is that what you said? Is that you? I can't tell who's speaking over there. So cool. So we're going to make a little tree, if you remember this, simplifying radicals. So we could take like the square root of something times the square root of something. What two numbers multiply to make 52 that we care about? 2 and 26 won't help us. What are they? Yeah, 4 and 13. Good. So we go 4 times 13. What's the square root of 4? So finally, that took a little longer than I meant for it to, but finally we can say this, that the modulus of the complex number 4 plus 6i is equal to 2 roots of 13. And if on occasion someone wanted that as a decimal, they'd certainly be able to ask, and then you could calculate or bebop it out and come up with some decimal. That's what modulus is all about. It's obviously a pretty short process. If you don't want to draw a picture, I can't blame you. So let's practice another one and see if we can be quicker. What's the modulus of 4 minus I? It's very quick. What's 4 squared? What's 1 squared? What's 16 plus 1? There you go. So the modulus of this particular complex number is just root 17. Lickety split. No need to draw Pythagorean triangles and all that. I was just trying to remind you of what the process is. Right. How about this one? What's the modulus of 15 minus 8i? Forget negatives. When you do modulus, negatives don't matter because we're squaring stuff up. What's 15 squared? I heard it. No. 225. Very good. Did you say 09? 8 squared? 225 plus 64? 289. And the square root of 289, who's good with their facts? What is it? Uh-oh. That's the square root of 169. Someone whispered it. Oh, I see. Now we're going to prank. Okay. You're going to whisper answers and then be like, I didn't say it. Good at 17. Whoever said that. Thank you. 17. Sometimes the modulus is just an ugly root, like the problem up at the top of the board. Sometimes it comes out to a nice whole number value, and sometimes it's just a simplified radical factor. How about this one? What's the modulus of 6i? Now, if you understand the definition of a modulus, that whole distance idea, where is 6i? If you had to graph it, where would it go? Nope. Just up 6, just straight, quick journey upwards, no sideways because there's no real part. So what's the distance to get from the center up to 6? This was simple. Don't make a math problem out of something like this. The modulus is just 6. You can make it a math problem if you really wanted to. And then, of course, finally, you can do the modulus of a real number like -10. What's the modulus of -10? It is just 10. All right, so that'll get us through the first section. Any questions so far? How much time do I have, by the way? There 104. Oh, am I going too fast or are you guys doing okay? You good? Okay, good. Adding complex numbers. How about 5 minus 2i plus -8 plus 10i? How do you add two complex numbers together? Combine like terms. That's it, the long and short of it. So, and in a case like this, since there's addition in the middle, there's no need to show any work. It's just literally put the like terms together. What would the real part of my answer be? Nice. And what would the imaginary part of my answer be? Plus 8i. So adding is pretty simple like that. Pretty hard to think that we could mess that up. It happens from time to time, but that's pretty simple. It doesn't get harder necessarily when we do subtraction. It just gets missed a lot more because people think that they should skip steps. So if I do a subtraction problem like this, you'd be probably pretty amazed at how it seems like that should be equally simple, right? But the miss rate goes exponentially higher. And the reason is, because this is your third algebra class or third math class, is that we're distributing a negative, right? So whether you show your work on something like this or not, it's important to understand that this minus sign doesn't only affect the 11, but it also, of course, affects this. So we could do this mentally. What's our real part going to be? -7. That's the easy part. Watch out for this part. What's the imaginary part going to be? Good job. What happened there is we distributed the minus sign as a negative. It turned the -6i into a +6i. So that's adding and subtracting complex numbers. Still good? All right, let's get to multiplying. I think I'll probably stop after multiplying today, and then we can do a little bit. Yeah, we'll do first page today. Yeah. Anyone remember how to do this? How? Yeah, it's like FOIL, like multiply, right? Let's knock this out. I'd love the color coding. So here it goes. Brady got us going. Here we go. I'm going to start with the red. What's 5 times 3? Nice. Okay, I'm going to switch over to purple. What is 5 all the way across times -3i? Beautiful. Let's head to green now. The green is right here. What's 2i times 3? Beautiful. And then finally we have yellow. What is that? Nice job. I'm going to go ahead and assume you don't have any questions about step 1. It's usually this step where people get a little confused. But again, this is your second go around, so there shouldn't be any major issues. Who remembers the answer to what this is? It's not 1. Yes. This is where the whole meaning of imaginary numbers kind of comes crashing down on you. Like, wait a second, did I just square something and get -1? Yeah. And that comes back fundamentally to the idea of what I is. I is exactly the square root of -1. And so if you square that, Square root sign goes away. This fundamental fact in the white box is really what carries us through. So I squared equals -1. So this little white bubbly part right here takes on the value of -1, which then means that this big white box takes on the value of what? +6. Very good. So what's the final answer to this problem? I don't know what you just said. Yes, 21 minus 9. Jackpot. Remember that? Okay. Let's do another one. Do another one. I squared is really easy. He's just a sign changer. I squared's like, I'll just change it from a minus to a plus or a plus to a minus. Piece of cake. Let's go again. Give me a complex number. Hayden, write me a good one.
Oh, 21 minus 9i.
Oh my God. Okay, someone else give me a complex number. Thanks for those huge numbers. That was what? Thank you. He saved us. He brought us back down. Hayden went Astro Boy. So let's make sure if you don't know, just ask and we'll slow it down for you. So remember, it's just a 4-step process. So let's begin with Mr. Red. What's 21 times 1? Good job. And we'll head over to Mr. Purple. Purple's the way outside one. So what does that make? Yeah. Then we're going to head to green, which is the 2 closest ones. What's that make? Yeah. And then we'll do yellow, which is back and back. So end. What's that? And we should get to the point where instead of writing plus 9i squared, just write -9. And again, that's that idea, that quick fluency about what does I squared do? He just changes signs. So he takes what would have been a +9 and makes it a -9. Just cut right to it. What's the final answer here? 18. Did you say 18? Holy crikeys. 12 minus 30. Any questions so far? Did that feel better? Just a little? Okay. Emma, you remember this? Hayden?
Absolutely.
But you're doing okay?
Oh.
You're up. Okay, cool. How about these? What is special about those? They're exactly the same except for the verb in the middle, right? One has an action word of plus and one has an action word of minus. And so that makes something cool happen. Let's see what it is. We'll run through the whole 4-step process. And then in the future, we won't go through as much work on something like this. It should be quick. The answer will maybe surprise you. We'll see. So what is 5 times 5? Okay. Now this purple and greens are going to be of massive significance. What's purple make? Nice. And green will make what? Will that always happen in a situation like this? Yes. Definitively 100% yes. If you write these particular types of complex numbers, I'll tell you what they're called in a second, unless you remember, they have to always have 1 plus and 1 minus that will perfectly kill each other. So pretty cool. And then yellow will not go anywhere, but yellow, we're pretty familiar with what to do with this guy. What really is yellow? Good job. It would be -36i squared. Way to get right to it. It's just actually +36. And then, of course, we're within our rights to take the purple and the green and say, well, you guys are going nowhere. Interesting that these types of complex numbers, when we multiply them, will equal a real number. And that will always be the case. These, by the way, are called complex conjugates. So watch out for them. And the last one, and then I'm going to give you a little bit of work time, that we're near as much as I intended to, but we should be able to get through the front page and then we'll do the back page tomorrow. So The only other thing that you will see is just a shortened version of what we just learned. I was gonna ask Hayden, but he's gonna bust out something like 56 plus 38i. Let's ask go ahead, Meat Patty, what you got? Give me just a complex number. Don't go all Hubbard on me. 8 plus 4i? Is that what I was said? Like, it's the air conditioner. It's noisier than you think. There you go. This math problem should conclude today's lessony part. So let's get to it. What does it mean to square something like this? Yeah, you just multiply it by itself. These are not conjugates, nothing cancels. It's just literally asking us to do 8 plus 4i times 8 plus 4. And there are shorter ways to do this, but you just kind of develop those, learn those as you go. So that's what it looks like. Can anyone do this quickly in their heads? Just pop right to the answer? I would be impressed. What's 8 times 8? What's 4 times 4? So again, 16. So we have a decision to make now. Notice I've gone a little bit out of order and I've stopped using colors. If you do the first ones multiplied and the last ones multiplied, that's where your real components are always going to come from. So is this 64 plus 16 or 64 minus 16? It is minus because the plus 16i squared is going to get like hijacked. And what is 64 minus 16? So our real part is 48. And then to find the imaginary part, you just do your inners and your outers and add them together. What do the inside two make close together? What do the outside ones make? Exactly. They're just naturally destined to be exactly the same. So 32 eyes plus 32 more eyes makes 64 eyes. And I do see some of you trying to do that mentally. Kudos for the effort on that, because those can be done pretty quickly, I think. That's it. The rest of this has division, which I'm not feeling that. This is not the right time to just keep going. And then there's powers of I, like I to the 3000th power. We'll talk about those two things tomorrow. So in the meantime, I'm going to hand this out. I would like you guys to get the front page done. That will be my only expectation for today. Got it? Right. And I couldn't say this the last time I met all of you guys in class, but now I can say, hey, since you've taken geometry, what a nice thing to be able to say. You guys might remember these things called Pythagorean triples. Here's an example of a Pythagorean triple. Yes, I am helping you with number 3, I promise. 3, 4, 5 is called a Pythagorean triple because it just so happens, like if I gave Dugan a set of sticks that were 3 feet long, 4 feet long, and 5 feet long, if he arranged them into a triangle, the angle between the 3 and the 4 would be a right angle. So by definition, 3 squared plus 4 squared equals 5 squared. Any set of 3 numbers for which that condition is true is called a Pythagorean triple. Another example of a Pythagorean triple you saw in the lecture today was 8, 15, 17. Those 3 numbers, when working in harmony, will always make a triangle with a right angle. Another example of a Pythagorean triple, this will help you a lot when we get to trigonometry, is 7, 24, 25. And Bryn's going, I still don't know where you're going with this. Well, it just so happens that there is another Pythagorean triple that you should be familiar with, and his name is 5, 12, 13. That is a Pythagorean triple. Now, if you don't know why I'm talking about this, it's because look at the fourth problem. Did you say the third problem? Oh, crap. I'm talking about the fourth problem. I might as well finish this now. So if we're, I'm sorry, I forgot. So if we're on the fourth problem and we do these 3 numbers, we can already look at that and say the answer is 13. But if you wanted proof of it, you take your -5, square it, you get 25. Take your 12 squared, you get 144. Add those together, you get 169, square rooted, and whoop, as advertised, 13. Now let me answer the actual question that was asked, and that is problem 3. In problem 3, the numbers in the problem are 1 and 1. Oftentimes, if you get a question like this, it's because we're not able to see that 1 with the red arrow pointing at it, but it's there. So if we just take the numbers and square them and add them, the bark is way bigger than the bite here. What's 1 squared? What's 1 squared? What's 1 plus 1? So the answer is the square root of 2. Got it? That means if you left the complex origin at 0, 0 in the center and traveled right 1 unit and up 1 unit in the complex plane, the distance to that point would be the square root of 2. 1.4-ish. Leave it as roots. Simplified roots.